Okay. So I think it's time to start with next talk. Next speaker is Daniel Harlow from MIT, and he will talk about continuity of symmetry operators in quantum field theory.
Yeah, hi everyone. Buon pomeriggio. Thank you for the invitation. It's nice to at least virtually see all of you. I should say this, I don't have too many slides here, so I'll go slow and I'm happy to answer questions during the talk, make things a little more lively. I also wasn't totally sure about, what to talk about for this audience, so I tried to pick something that was a little bit more mathematical. I'm a bit of an outsider in this field of mathematical quantum field theory, so I apologize if there are references missing, and I'm happy to learn more about other work that I should be mentioning. Okay, so I'm going to talk about this rather general sounding topic of the continuity of symmetry operators in quantum field theory. I'm going to be talking entirely about global symmetries, not about gauge symmetries. Gauge symmetries are also interesting, but I'm not going to talk about them in this talk. And I'm going to focus on internal global symmetries. So those are symmetries that don't move the operator algebra around. They just send all the operators in one point to another operator also at the same point. So when you have a quantum field theory with a global symmetry, there are two different actions of the symmetry group which are interesting. So there's the action on the states of the theory, right? So we have a homomorphism U from the group to the set of unitary operators on V, where V is the Hilbert space of the theory. And like I said, U of V is just the set of unitary operators. Okay, so this is the unitary operators that implement the symmetry on the states of the theory. Okay, so that's one of the actions of the symmetry. The other action that's interesting is the action on operators. So given a U, it induces a map FU. So for any spatial region R, you have this map which takes an element of the group and an operator in the algebra. So A of R is the algebra of bounded operators with support in R, okay? And then this F takes an element of G, an element of A of R, and maps it to A of R, and just in the obvious way. So you just conjugate the operator O by U of G, okay? So this is the action of the symmetry on the operators of the theory in any region. So in this talk, what I'm going to consider is the question of what kind of continuity properties we should require of this map U and this map FU, which is something that I haven't really seen discussed too explicitly before. We'll see that there are some interesting questions that come up, and I'll try to give answers for what I think are the right continuity properties for these maps. And so this talk is based on work with Hiroshi Oguri from Caltech and IPMU. So in this paper, it's a long paper, and mostly we were thinking about quantum gravity, but along the way, we ran into this question of the continuity of symmetry operators. So basically, we were trying to prove various old conjectures about constraints on symmetry and quantum gravity. And to get those arguments to work, we had to be careful about the continuity of these operators. But today I'll just talk about this. It's an interesting question in mathematical quantum field theory. I won't try to connect it to quantum gravity unless you want to ask me about it. Okay. I see no questions so far. So let me summarize what the results will be, and then we'll get into how we arrive at them. So the first thing, and this will kind of be the first one will kind of be more of an axiom than a result, although I'll try to motivate it. So that if the symmetry G is not spontaneously broken, then we should require that U be continuous in the strong operator topology. So I'll try to motivate that, but in the end, that'll sort of be an assumption. And then we'll see that that implies that for any bounded region R, so finite spatial region, not all of space, the restriction of FU, the action on the operators, So if you restrict it to any uniformly bounded subset of A of R, then this restriction of F should be jointly continuous as a function of G and A of R, where we put the strong operator topology on A of R. So in particular, there's this kind of funny restriction to uniformly bounded subsets, which comes out of this, which maybe was a little bit surprising to us when we were first thinking about this. So this will be the situation when the symmetry is unbroken. On the other hand, if the symmetry is spontaneously broken, then we'll argue that there should be no continuity requirement on U, the action on states. But we will nonetheless still require that FU, the action on operators, has this funny requirement that its restriction to any uniformly bounded subset of A of R is jointly continuous with the strong operator topology on A of R. And that's for finite bounded regions. Moreover, we'll see that in the unbroken case, we can improve the situation a bit in terms of this restriction on uniformly bounded subsets. So there's a modified topology we can define by using the vacuum, the invariant vacuum state. And with this modified topology on A of R, then we'll just see that F is continuous period, jointly continuous period without any restriction of its domain. And moreover, we'll see that in this case, F defines a unitary representation of the symmetry group G. So as an application of this, we'll see essentially immediately from this last result that if you have a quantum field theory with an internal global symmetry G, where the fields transform in a non-unitary representation of G, then the symmetry must be spontaneously broken, which is kind of an interesting dynamical statement about quantum field theory. I would say most people probably expect this to be true, but using these ideas, we can prove it. So that's it for the introduction. Let me pause and ask if there are any high-level questions about these results or the motivation or anything else.
Sorry, there is a question.
Yeah.
Can I stop from?
How do you define broken symmetry?
Broken. Oh, yeah. How do I define broken symmetry? Yeah. So I'll get into that a little bit more, but the idea is that the vacuum of the theory is not invariant, and so we have a set of superselection sectors which are labeled by the different vacua, and this U acts in that larger Hilbert space. It doesn't act within each superselection sector separately. I'll discuss that more in a minute, but if you have follow-up, I'm happy to respond. Yeah, I should be clear that I don't mean explicit breaking of the symmetry, right? So if the symmetry is just broken because you add a term to the Lagrangian that breaks the symmetry, for example, then it will not be true that the symmetry sends vacua to other vacua, right? So when I say spontaneously broken, it still is a symmetry, right? It commutes with the Hamiltonian.
Okay, I think
yeah.
you can continue. Thank you.
So okay, so now let's get into the details a little bit more. So we first have to define more carefully what we mean by global symmetry. So this was one of the things that we did in this project, and so I'm going to propose a rigorous definition, or at least to my taste, rigorous, of what we mean when we say that a quantum field theory in these space-time dimensions has a global symmetry with a symmetry group G. Okay. And G you can think of as a Lie group. Although I think for everything I say in this talk, it's enough to assume that it's a topological group. So the first requirement, kind of the obvious one, is that there should be a unitary homomorphism U from G to U of V on the Hilbert space of the theory quantized on the spatial manifold RD minus 1. Okay, so probably we all agree that at least this should be true. Okay, remember we're talking about internal symmetries here, so we don't have to worry about anti-unitary operators. So this is kind of this is true sort of in any quantum mechanical system. We would probably require this. In quantum field theory, there's an additional requirement that the symmetry has to respect the local structure of the theory. So in particular, if you have any spatial region R, then this homomorphism under conjugation has to preserve the algebra of operators in R. So the symmetry can't take an operator here and move it to an operator over there, or take an operator here and move it into some big non-local mess, right? So here for internal symmetries, it just has to preserve the algebra of operators in the region. In principle, we don't have to require this, but symmetries that don't obey this are sort of not interesting in quantum field theory. They're not constraining enough to be useful. If you want an example of something that that doesn't obey this, right, you could take the symmetry which is generated by the square of the Hamiltonian. Okay, but that's kind of a silly symmetry to talk about in quantum field theory. And so moreover, right, there's this continuity requirement that I mentioned that for bounded regions, the action FU of the symmetry on the algebra should have this continuity requirement of being jointly continuous on uniformly bounded subsets of A of R. And so I'll motivate that more soon. Okay, but that's not enough. These are two requirements. There are two more. So there's a faithfulness requirement. This is just to make sure that we've correctly identified the symmetry group G. So the requirement is that for any region R and for any G, which is not the identity, then there is some operator O in A of R such that the action of the symmetry on the operator is not trivial. Okay. So this is just making sure we got the symmetry group right. I mean, if we didn't have a requirement like this, then anything could be a symmetry, right? It just acted trivially on the operators, and that'd be boring. Okay, and so actually, in my experience, kind of for example, in most discussion of symmetry in algebraic field theory, roughly speaking, these are the three requirements. But then I would actually add a fourth requirement, which is conservation, which says that if you act with a symmetry on the energy momentum tensor, then it's invariant. So you just get back the energy momentum tensor at the same place with the same indices. And so this, maybe in the kind of modern language, we would say that this symmetry operator is a topological surface operator. So you can deform it around however you like in correlation functions without changing the result of the correlation function unless it crosses another operator. But you can also just say this is sort of local conservation of the symmetry. And so I want to emphasize I'm not assuming that the symmetry is continuous here. So this is the definition, even if G is discrete, like it could be Z2 or something. And this I would claim this is still the correct definition. Okay, any questions about this definition of global symmetry in quantum field theory?
No questions for the moment.
Hopefully not.
Maybe I have a short one.
Sure.
So your algebras, are sister algebras for Neumann algebras, because this is.
I'd say von Neumann algebras. Yeah, acting.
Von Neumann. Okay.
Von Neumann algebras on V.
Okay. Yeah. Thank you.
Sure. Okay, so now let's talk a little bit about spontaneous symmetry breaking. So I want to emphasize this definition here was completely algebraic, right? We only discussed how the restrictions that we put on this U only constrained how it acts on the operators. They didn't say anything about how this U acts on the states other than that it has to be a unitary homomorphism, all right? And so in fact, I would like to include spontaneously broken global symmetries. I would say they're included in this definition. But to include them, we need to sum over the vacuum sectors in the Hilbert space V. So because the symmetry moves you from, in the Ising model, the state where all the spins are up to the state where all the spins are down. So if we want U to act on the Hilbert space of the theory, we have to include both the up vacuum and the down vacuum in the Hilbert space, which people sometimes don't want to do, but I think here it's much more natural to include it. However, when G is discrete, that's fine, right? You just have a direct sum of up, down. But when G is continuous, like say U1, or SU2 or something, then there's something that's a little bit weird that can happen. And so I want to explore this weird thing that can happen. So let's do it with an example. So let's say we have some periodic field, with period 2 pi. So theta goes to theta plus 2 pi. And let's say that theta gets an expectation value in the ground state. So then we have degenerate vacua, which are labeled by this expectation value of theta. Okay? And then if we act with this symmetry operator, U of G, so here the group is just U1, so it's U of a phase. then it just shifts the vacuum by phi, okay? But then you see there's something funny going on with the continuity of U, because the states theta and theta plus phi are orthogonal quantum states for any non-zero phi, which means that even if this phi is very small, you're very close to the identity in the group. As long as you're not exactly at the identity in the group, then you move by a lot in Hilbert space. You move to an orthogonal quantum state. Okay. So in perturbation theory, the way this orthogonality shows up is that there are infrared divergences when you try to compute matrix elements involving this U operator. And you need, basically these infrared divergences enforce that these two states are indeed orthogonal. And so actually these divergences are sometimes misinterpreted as saying that U of G doesn't exist. But this I think is really wrong. It clearly does exist. Here's how it acts on the vacuum. And then you can figure out how it acts on any other state because all the other states come from a vacuum state by acting with the local operators. And then you can use the action of U on the local operators plus this action on the vacuum to define U. So it clearly exists. There's no infinities in these formulas, right? But the right statement is that the map U, the homomorphism from G to U of V is not continuous, okay, in the case where you have a spontaneously broken continuous symmetry. And so somehow this is a little bit weird. This was the puzzle that was bothering us when we were first thinking about this. And so then we started wanting to understand better, okay, well, if sometimes U is not continuous, then when is it not? What about FU? What should its continuity properties be? And so that was how we got into the stuff that I'm going to tell you about now. But I'll ask any questions about this, comments about spontaneous symmetry breaking.
No
All
questions
right.
for the moment.
No questions. Good. Okay, okay, now, sorry, I apologize for probably most of you, this slide is unnecessary, but I just want to make sure we're all on the same page in terms of notation. So let's just run through some standard terminology. Okay, so any Hilbert space V comes equipped with what I'll call the standard topology. Maybe it has another name that I don't remember, which is defined by using the norm, which is just the square root of the inner product. Okay, so that defines you can define a metric on V by using this norm, and then it defines a metric topology. Okay. So we'll say a linear operator O on V is bounded if there is some C greater than 0, such that the norm of O acting on V is less than C times the norm of V for any V in V. Okay, and then we'll refer to the set of bounded operators on V as B of V. Now here's this word that I used several times already, so this maybe pay attention, maybe it's a little less standard, although hopefully the name is clear. So I'll say that a subset of B of V is uniformly bounded if there exists a single C such that all of the O and M are bounded by the same C. Okay, so this is certainly not true for B of V as a whole, right? You can find operators whose norms are arbitrarily big in B of V, but in a uniformly bounded subset, you can't, okay? And so that is going to be important in theorems that follow. So this will be a restriction. Only some subsets of B of V will have this uniformly bounded property. Okay, then for any operator O, we can define its norm, the operator norm, as the smallest C, such that OV in norm is less than equal to C times the norm of V for all V and V. Okay, so that's a completely standard, I think, definition. And then finally, we can use also this operator norm to define a topology on B of V, right, which is the kind of the obvious topology on B of V. You just, you construct a ball of radius epsilon around any operator O naught by just taking all the operators in B of V where the operator norm of the distance of O minus O naught is less than epsilon. Looks like there's a question. In the operator, well, I think the operator norm is kind of uniform by definition, right?
Just a moment. No, it seems that there is a question. I have to...
Yeah, I'm looking in the chat. It says, "Is uniform boundedness just boundedness in the operator norm?"
Okay.
But I'm not sure, because uniform boundedness is a property of a set of operators, right? Whereas operator norm is a
Yes.
property of a single operator. If I understand, maybe I think the answer is yes, though, if I understand what you're getting at. Yeah.
No, I think the answer is yes. It's just,
Yeah, I think the answer is yes. Yeah,
yes, it's the same.
that's right. Well, it's saying that all the operators in the set have an operator norm, which is less than C. That's what it's saying. Okay, I can say it that way. Yeah, so maybe I should have given this definition first and said this one that way, but it's okay. All right. So okay, so that hopefully all that is standard stuff. Unfortunately, this norm topology is much too strong for quantum field theory. You know, if we demanded that things were continuous, this U and F of U in the norm topology, then nothing would ever be continuous. So just for example, if you think about like a free complex scalar field with a global symmetry that's a phase rotation like this, right? So then there are states in the Hilbert space of arbitrarily large charge under this phase rotation, right? Because you have particles that are labeled by integer charge, so you can have as many particles of positive charge as you want. And then thus for any non-trivial element of U1, there will be some states where the action of that element of the symmetry is large, okay? Because you just, however close you are to the identity, you just make the charge really big. And now you have a state where the symmetry acts in a big way. So this U of G is, so certainly the U of G for this symmetry is certainly not continuous in the norm topology, even if the symmetry is unbroken, right? Never. So this kind of has nothing to do with the issue we had with spontaneous symmetry breaking. This is just a basic problem with the norm topology, and so presumably, nobody talks about the norm topology in quantum field theory, I guess, at least not for defining the continuity of maps. Okay, so to fix this, we have to introduce also another thing, which I hope also is, I guess, is standard for everyone or most people, which is this idea of the strong operator topology. So there, instead of generating the topology using balls of the uniform norm, you use balls which are labeled by both an operator and a state. Okay, and so the idea is that you have a ball of radius epsilon around an operator and a state, where you say that the Hilbert space norm of O minus O naught acting on this state has to be less than epsilon. Okay, and if so, then you're in the ball. And then strictly speaking, this is not a basis, but then you take finite intersections of balls like this, and that gives you a basis for the strong operator topology. And so the advantage here is that of this topology is that for U of G to be continuous in the strong operator topology, we only need U of G acting on V to be a continuous function of G for each V. So we act on V with U of G. We pick a state, then we act with the symmetry, and then we move around where we are in the group holding the state fixed. Okay? And that's a much easier kind of continuity to have than continuity in norm topology. Indeed, you can check, so it's just a little bit of algebra, but in this complex scalar example, you can just check that any normalizable state in the Hilbert space of this complex scalar will have the property that U of G acting on it gives you a continuous map from G into the Hilbert space. So basically, because since the state is normalizable, the contributions from large charge eventually have to be suppressed in the state as much as you want for any fixed state. Motivated by that example, and also by something I'll say on the next slide, I'm just going to take it as an axiom that if you have an unbroken global symmetry, then U of G should be continuous in the strong operator topology. So I'll pause again to ask if there are more questions. You can also type them in the chat.
I don't see questions. No.
Okay.
No questions for the moment.
Good. So let me also now try to motivate this.
Sorry, Daniel.
Yes.
There is a question.
Yeah.
I don't understand whether you assume that U is one parameter. It's a group or just a projective representation or something.
I said homomorphism. So to me, that means it's not projective. It means U of G1 times U of G2 is U of G1, G2. Yeah, that's another talk I could give. I claim that in quantum field theory, you never really have projective representations of global symmetries. This is not a completely uncontroversial statement. There's an appendix in our paper where we try to make the case for that.
Another question?
Are you only discussing continuous symmetry?
No, I'm continuing both continuous and discrete. So G, so yeah, maybe I should clarify. So when I said that G was a Lie group, for me, a Lie group is allowed to be zero dimensional. I think that's correct, right? But the definition of a Lie group allows it to be zero dimensional.
Yes, countable.
Yeah. Okay, no one else? Okay, so so now I want to get back into this. Well, actually, yeah, so someone just asked, right? So far I've been demanding that U is a homomorphism. Okay. Now you could say, why did I say homomorphism instead of representation, right? Usually when we talk about symmetries, we say there's a representation of the symmetry group acting on the Hilbert space. Right? So the reason I didn't say that is because in the representation theory of topological groups, you only say that a homomorphism is a representation if it's jointly continuous. If this map phi, where it's a map from the Hilbert space and G to the Hilbert space, which is defined in the obvious way, you just act with U of G on V. You only call this a representation if it's jointly continuous with the standard topology on V. Okay. You know, many sort of famous theorems in the representation theory of groups on Hilbert spaces use this joint continuity. Okay. Whereas in the discussion that we've been having, right, we've seen cases where U is maybe not continuous, and so then we don't necessarily get to call it a representation, and we're left just calling it a homomorphism. Okay. But there's a useful theorem which tells us that actually this this map phi, defined like this, is jointly continuous if and only if U is continuous in the strong operator topology. So here's what the theorem looks like. So V is a Hilbert space, G is a topological group, and U from G to U of V is a map. In fact, for this theorem, we don't even need to assume it's a homomorphism. It's just some map from G to U of V. So then phi, this phi of G comma V is jointly continuous if and only if U is continuous in the strong operator topology. And so we can think of this as like another motivation for the strong continuity of U as being the right criterion, is because this is exactly the criterion that lets us use the machinery of representation theory as it's usually defined on infinite dimensional Hilbert spaces. So I'll just pause for a sec if there are any questions or comments about that. We're doing fine on time, so it's okay having questions. I don't have that many slides.
No.
Okay.
Sorry.
If the group is Z2, what is the continuity in G?
Oh yeah, good. So the continuity is pretty easy if G is Z2, right? Because we just have it's the discrete topology on G, so everything is continuous, right? Yeah, yeah. So the continuity is kind of more interesting in the continuous case, but the definitions that I'm giving apply either way. Okay. So I've kind of now introduced my main sort of axiom or principle. I've tried to motivate it in two different ways, which is that U should be strongly continuous when the symmetry is unbroken. So now let's learn what that says about FU, the map that gives the action of the symmetry on the algebra. Okay, so here's the theorem. So I'm not going to give the proofs of any of these theorems. I guess most of you can, if you read the theorem and think for a little bit, you can probably prove it. So I'll just quote all the theorems. Okay, so let V be a Hilbert space, G a topological group, and U from G to U of V a strongly continuous map. Okay. So then the restriction to any uniformly bounded subset M contained in B of V of the map FU which is defined by this conjugation, right? U of G dagger O, U of G, is strongly continuous. Okay, so this is this continuity requirement I mentioned before on FU, but now we see that it is the continuity of FU, which follows from U of G being continuous in the strong operator topology. Okay. And when we were writing the paper, we were a little bit frustrated with this restriction to any uniformly bounded subset of M. But well, you'll see that in the unbroken case, there's something I can do about it later. But in general, it seems we're stuck with it. If you try to just have it be continuous in general, it doesn't work. So the proof of this theorem and the previous one are simple. Like I said, you basically just use the assumptions plus the triangle inequality. Okay, depending, yeah. I guess the same thing you always do in these analysis kind of proofs. And so, like I said, this the output of this theorem is precisely the continuity requirement which I imposed on FU in the definition of global symmetry. But here this can be viewed as the motivation for it, at least in the case where the symmetry is unbroken. But in fact, even when the symmetry is broken, in which case U of G is not strongly continuous, nonetheless, for bounded regions, the action of FU on the algebra shouldn't care whether the symmetry is spontaneously broken or not. It might care for, if you take R to be, infinitely big or something, right? Then you can learn about the spontaneous symmetry breaking. But the usual understanding of spontaneous symmetry breaking is that the action of the symmetry on the states is different, but the action of the symmetry on the operators is the same. Okay, and so that's why we said that even in the spontaneously broken case, this continuity property of FU stated here should be true. Because if you look really locally, at what's going on in a small region, you shouldn't be able to tell whether the symmetry is spontaneously broken or not. Okay, and so with that justification, we just in general take the output of this theorem to be the continuity property we assume for global symmetry, even in situations where actually the assumption of this theorem that U is strongly continuous do not hold. Okay, any questions about that?
I have one. So because maybe I don't remember, when you say strongly continuous, the action on operators, you means that the topology on the operator is the strong topology, I think.
Yeah, right. So
not the norm topology. Okay.
That's correct. Yeah. So this map F is a map from G times B of V to B of V. Okay. So what I have, so that when I say that FU is strongly continuous, what I mean is that if I put the product topology on G times B of V, where I put the strong topology on B of V, and I put the strong topology on B of V here as well, then this map is continuous.
Okay, thank you. No, it's not so standard, because when you say strong topology on a sort of
I know.
space, you mean that. But
yeah, I wasn't sure how to say it, but it's a mouthful if every single time.
No, it's okay. It's okay. It's important is the concept. Thank you.
Yeah, sure. All right, very good. Okay, so we can also further motivate this by seeing what we can learn in the other direction. So say instead we assume that we have this uniform, strong continuity on uniformly bounded subsets. Say that we just assume that that's true of F of U, as we did in our definition of global symmetry. Then we can ask, what does that tell us in the other direction about U, right? The symmetry, the action of the symmetry on the states. Okay. So in general, it tells us nothing, which is good, because we have this example where the symmetry is spontaneously broken, where FU obeys to this continuity requirement, but U is not continuous at all. Okay. But if we assume that spontaneous symmetry breaking does not happen, meaning we assume that we have a vacuum state which is invariant, okay, then this theorem I just quoted has a converse. And so here's the converse. So I let V be a Hilbert space, G a topological group, and moreover, I say that there's some subalgebra A of R. I call it A of R, but this is just a math theorem, so we don't have to think about quantum field theory. It's just some subalgebra B of V, von Neumann subalgebra, if you like. And U is a map with the prop from G to U of E as a map such that the FU that it induces is strongly continuous on uniformly bounded subsets of A of R. Okay, so here I'm just assuming that FU has the continuity properties we want. But I also assume that there exists some state in V which is cyclic with respect to A of R, right? Which means that that the set of states you get acting on omega with A of R is dense in the Hilbert space, okay? And moreover, I assume that omega is invariant in the sense that if I act with U of G on omega, I get back omega for any G, then U is strongly continuous, okay? So what this theorem says is that our continuity condition on FU is not too weak, right? It's not like, strong continuity of U implies this plus something else, right? This is strong enough to give us back the strong continuity of U in the other direction, provided that we assume that the symmetry is unbroken, meaning that we have this cyclic vacuum, which is invariant under the symmetry. Okay, and so I think this sort of makes it quite clear that this restriction on FU is the correct one. Okay, any questions about that?
There is a question, just a moment.
I think here you are assuming the cyclicity of AR, but when you gave the example of like shifting the charge, I think the local algebra not the vacuums are not cyclic for the local algebra. Is it correct?
Oh well, okay. This is a bit philosophical. So when I define the local algebra, I include operators that are charged under a global symmetry.
Yeah.
So yeah, I definitely, I mean, otherwise, if we go back to my definition, right? So this is maybe a philosophical disagreement, maybe. So I defined the algebra, I defined the symmetry to act non-trivially on A of R. You see, I required that for any G, which is not the identity, there's an O that transforms, okay? So I do not, so I would say that when you, projecting onto the set of invariant states is, I would say, something you do for a gauge symmetry. It's not something you do for a global symmetry. When you have a global symmetry, the states which are charged, I would say, are physical. And you get them by acting with elements of the algebra. So you might say it's a definition. I'm just including charged operators in my A of R. Is that okay?
But if you include the charge operator, I don't think the unitary, the adjoint action of the unitary is acting continuously on the charge transporting field.
No, I think it is. That's kind of what we're discussing, right? So like if you, well, the continuity requirement is the one I'm saying, right? It's that FU is strongly continuous on uniformly bounded subsets of A of R. Okay, that's the statement which I think is true.
Okay, I will think about that.
Yeah, I mean I mean this is an important question. I know that in historically people sometimes like to not include charged operators in the algebra, but I think the theory is much more elegant if you include them. You just have to think about what it means. Okay. So actually, in the situation, so that's actually a good segue into the last topic. So this restriction to uniformly bounded subsets of A of R is kind of annoying, okay? And actually, in the case where the symmetry is unbroken, there's something we can do which is better, and in fact, which will give a continuous action in this other topology. Okay, so let me try to set that up. So this section is only going to be for unbroken symmetries. For broken symmetries, we're just stuck with the story I just told you. So let's begin by noting that let's say that we have some state omega, which is separating with respect to the algebra to the algebra A of R in some region. Okay, so separating means that there aren't any elements of A of R which annihilate the state. Okay, so if that's true, then actually you can define an inner product on the algebra A of R by just using the expectation value in the state omega, right? So when I write the parentheses with the omega here, that's the inner product of two operators. But then it's just defined in the obvious way, where I act with this operator on the vacuum, I act with that operator on the vacuum, then I take their inner product in the Hilbert space. Okay? And so you can check that this defines an inner product, and it's important that it's separating, because that makes sure that the inner product is only zero you know that the norm is only 0 if the operator is 0. And so then once we have an inner product, we can of course define a topology, right? Just by using the balls defined using that inner product. So actually these balls are a subset of the balls we used in defining the strong operator topology. So let me remind you that for the strong operator topology, the balls looked like this. So they were labeled by an operator and a state. And the rule was that the action, you know, an operator is in the ball if we take its difference with O naught and act on V naught, then it's less than epsilon in the Hilbert space norm. Okay. So we just take this definition, but we choose V naught to be our separating vacuum. And then that defines a topology on A of R, okay, which I'm going to call the vacuum topology. And since these are a subset of the balls that we use to define the strong operator topology, this is a weaker topology than the strong operator topology. And in particular, that means it's easier to be continuous, okay, which we like. And so in fact, there's a theorem. So this is kind of a mouthful. So we'll talk it through slowly, but essentially what this theorem shows is that the situation is very nice with respect to this topology. Okay, that's the summary of the theorem. It's very nice. Okay. So let me now go through it, right? So again, we have the Hilbert space V, we have a topological group G, and then we have some subalgebra A of R of B, and then we have this map U from G to U of V with the property that this F of U is strongly continuous on uniformly bounded subsets of A of R. Okay. So this first sentence here, these are the set of conditions which are true if we have a global symmetry according to the definition that I gave, including the continuity requirement on FU. But now let's further assume that there exists a state omega, which is both cyclic and separating with respect to A of R, okay, which we should be allowed to assume if R is a finite region, and also which is invariant under the symmetry. So U of G acting on omega is omega back for any G in G. Okay, so then here's what the theorem says. Okay, so first of all, then the restriction of FU to A of R is jointly continuous in the vacuum topology without any uniform bounded requirement. Okay, which is nice, right? It's just continuous. That's what we like, continuous. And in particular, if U is a homomorphism, which it will be for symmetry, right? Then, well, it's strongly continuous, as we already said. So that means it gives a unitary representation of. So U is a representation, but also F of U it defines a unitary representation of G on the Hilbert space A of R, endowed with this inner product, which is defined by the vacuum. Okay. So that's kind of a mouthful all at once. So we can just try to summarize, right? What this says is if the symmetry is unbroken, then the action of the symmetry on the operators gives a unitary representation of G. All right. The action on the fields is a unitary representation of G. So in particular, so you see, this means indeed, like I say here, so in the unbroken case, we can guarantee that the representation of the symmetry on the fields is unitary. And in fact, well, I didn't show you the proof, so you can't tell, but if you look at the proof of this theorem, it doesn't even require us to assume that elements of A of R are bounded. So in fact, we can apply this directly to the potentially unbounded fundamental fields that are appearing in Lagrangian, if there is one, you know, which is kind of nice, right? You know, as you know, for many reasons, you sometimes want to take A of R to be bounded, but in examples, it's nicer if you don't have to assume that, because the simple fields we like in quantum field theory are usually not bounded. And this theorem will still be true in that case. And so it will tell us that you know, even the unbounded fields have to transform in a unitary representation. Okay, so I want to emphasize that assuming that the symmetry was unbroken is really essential in the proof of this theorem. Okay, so as a counterexample, if it's broken, right? So like, let's think about a free massless scalar with a shift symmetry that just shifts phi prime equals phi plus a, right? So like a free massless has this symmetry. Oh, there's a question. Let me see. Greg asked, what topology on the unbounded operators? I think still the strong operator topology, Greg.
Yes,
so
domain, yes, of course. So the common domain.
Yeah, yeah, and right. So we can rewrite this. So we can rewrite this shift symmetry as a linear action on the set of operators, right, like this, right? So sometimes the shift symmetry is described as a nonlinear symmetry of quantum field theory, but this is a very misleading term because it's very linear. The action of the action on the operators is always linear. It can't be anything but linear. Okay, so it's weird when people call this nonlinear. Here's a way of making it clear that it's linear. It's just you have phi together with the identity, and you act on them with this two-dimensional representation of the symmetry group R, which is this symmetry of the shift symmetry. And just by looking at this matrix, right, you can see it's not unitary. So this is a non-unitary representation of R. Okay. And so what we learned from the previous theorem is that this symmetry has to be spontaneously broken, because if it wasn't, then we could have only gotten a unitary representation here. And of course, it is spontaneously broken. This is the standard fact about free scalar field in greater than 2 dimensions. In 2 dimensions, phi doesn't exist, so there's no discussion to be had. And so more generally, we learned that any internal symmetry which acts non-unitarily on the local operators must be spontaneously broken, which is sort of some interesting statement about the dynamics of quantum field theory. Okay, so that's actually all I had. Thanks for listening. I'm happy to take more questions about anything.
Okay, there is a question here.
Hi.
Hi.
I want, it's more a comment than a question, but for Neumann algebras, one usually deals with the topology of strong convergence on the pre-dual. So you have an action of the group by automorphism. You look to the pre-transpose on the pre-dual, and you require that it is a pointwise norm continuous.
Yeah.
I wonder what is the relation? With what you are doing?
Well, so yeah, I'm not sure if I can answer that off the top of my head. I mean, one fact about the strong operator topology is that it's the strong operator topology in some sense is the topology of pointwise convergence, right? So like if you have, I didn't write it, but let me go to the definition and then I'll try to say it. Where did I go? I went too far. Here, yeah. So the strong operator topology has the property that if I have a sequence of operators, O1, O2, etc., then it converges to an operator O in the strong topology if and only if that statement is true if you pick a state V and then you act with On on the V and hold fixed V, and then you ask if that set of states converges in the topology on the vector space, on the Hilbert space. So then that sequence of states converges for any V if and only if the sequence converges of the O's converges in the strong operator topology. So that sounds pretty similar to what you said, but I'd have to understand what you said better to see if it's the same or not.
Further questions or comments? Another from Roberto.
One more comment is that when we have a cyclic and separating vector, we have the standard implementation. So there is a canonical choice of the unitaries. Maybe this also can enter in your discussion.
Yeah, I guess. Well, that sounds similar to what this. So when you say the unitary, you mean on the operators or on the states? I can't hear. I'm not sure.
Okay, no comment, just speaking in the audience.
Yeah, that's probably it's related to this theorem, I guess. Yeah.
Okay, so let me ask a question about something that I looked at a very long time ago. That is the 5/4 theory with the Z2 symmetry.
Yes.
And there are different constructions. One is you can have a vacuum that's invariant under the reflection of the field.
Mhm.
That gives you a mixed state. And that mixed state can be decomposed. And this comes from the theory with a large coupling constant. And the mixed state can be decomposed into two pure states in which the symmetry is broken.
Sorry, how many dimensions, how many space-time?
Two dimensions.
2 plus 1 or 1 plus 1?
No, 1 plus 1.
Oh, 1 plus
It's
1.
like the Ising model.
Yeah, okay, that's fine. I just, yeah, because that theory is very different in 2 and 3 and 4 dimensions. So that's why I had to ask. Yeah, okay. So 1 plus 1, yeah.
How do you interpret your theorem in that case?
Okay, well, so so lambda phi to the 4th theory in 1 plus 1 dimensions is some nonlinear sigma model. Yeah, I'd have to be a little careful thinking about that because
And in the mixed state, the theory, the algebra is not irreducible. In the individual pure states, it is.
I'm a bit surprised that you say the vacuum is a mixed state. That doesn't sound like quantum field theory to me.
Well, it doesn't satisfy the Whiteman axioms, but it is quantum field theory.
Well, I guess this comes down to what we mean by quantum field theory. Why does, I mean, what, I would have thought this theory, yeah, I guess I would have thought this theory has a unique invariant ground state. I'd have to think a little bit about the limit, certainly a weak coupling.
If you construct the theory by starting in a finite volume and take an even state and pass to the infinite volume limit, you get the mixed state. If you take the theory where the field is at one of the minima of the potential, plus or minus, then you get the pure state.
Oh, sorry. Is the mass term m squared negative in what you're doing?
The mass squared negative is equivalent to taking positive mass and a large coupling constant.
Well, I mean, you said the potential has two minima, so that sounds to me like m squared is negative.
Well, that's the classical picture, but the quantum picture, you can take the m squared, the bare mass fixed and the coupling constant large, and you get two minima.
You mean in the quantum effective action? Yes. Okay, well, that's interesting. I haven't thought about that. I guess it's still hard for me to see.
Well, if you look back at our papers in 1975, you can see that this theory is constructed in two different ways. The first construction gave the mixed state. The second construction used a cluster expansion and gave the two pure states. And these have different physical properties.
Yeah, well, so we can certainly define a mix. Yeah, I mean, so we can, okay, I think what I can say is that my Hilbert space includes both of the two vacua you talked about because I summed over super selection sectors. So
so you always assume, but in quantum field theory, when you have different super selection sectors, you can, in field theory, you can decompose always into the individual sectors.
That's right, you can, but this U operator that I'm talking about will mix the sectors. So that's why I wanted to keep them all in the Hilbert space.
Right, but that's not what generally is done in Whiteman field theory, is to go to one of the individual sectors.
I understand that's what people like to do, but then you don't get to talk about this U of G. So I think it's better to do the direct sum so we can talk about it. I don't think you can stop me from doing that.
I can't stop you from doing that, but you get more structure the other way.
Well, no, I think it's a strict subset of what I get, right? Because I think your mixed state is kind of a mixed state between the two different vacua, right?
Yes.
So that's an allowed state in my larger Hilbert space. So all of your options are allowed states in my larger Hilbert space. So that sounds good, right?
Exactly.
Yeah. And the U of G acts in this larger Hilbert space. So if we want to understand U of G, we might as well talk about the bigger Hilbert space. Even though it's true that you can't mix from one sector to the other by acting with local operators. The thing is, this U of G is not a local operator, so it's allowed to mix them.
So my point is not that your theorem isn't correct. My point is that it's not the usual way of looking at field theory.
Yeah, I understand that. I think it's better.